In this lecture, we answer two questions. The first question, we find out the radius of this circle. And the second question, we find out the area of this green shape. So, we start with the first question. The point where quadrilateral ABCD that is described by this circle. Side AD of quadrilateral ABCD equals to 6 units in itself. Side AC equals to 5 units in itself. Side AB equals to 4 units in itself. Side BC equals to 4 units in itself. Again, our test is to find out the radius of this circle. So first of all, we define this angle BCD as alpha. Therefore, the opposite angle BAD must be equal to 180 degrees minus alpha. According to the rule that said that the sum of two opposite angles in a cyclic quadrilateral is equal to 180 degrees. So if this angle equals to 180 degrees, then 180 degrees minus alpha plus alpha is equal to 180 degrees. It is the sum of those two angles inside the cyclic quadrilateral ABCD. Therefore, this mistake must be equal to 180 degrees minus alpha. Yeah, in the drawing, we have quadrilateral ABCD that is described by this blue circle. The sum of those two angles, that is to say A plus B equals to 180 degrees, and the sum of those two opposite angles, that is to say X plus Y, also equals to 180 degrees. So according to the new rule, this angle must be equal to 180 degrees minus alpha. In the next step, we will join points B and D together by straight line. By joining points B and D, we divided quadrilateral ABCD into two parts. The first part is this upper triangle ABD, and the second part is the lower triangle BDC. So in the next step, we will implement the law of cosines on both triangles. That is to say, we will implement the law of cosines in the upper triangle ABD, upper triangle ABD, and then we will implement the law of cosines this lower triangle BDC. So a quick look of the law of cosines. First of all, the law of cosines is true in any triangle, so this is triangle ABC that could be any triangle. This angle BAC is equals to theta degrees in size. Side AB of this triangle ABC equals to 1 unit in itself. Side AC equals to B units in itself. Side BC equals to C units in itself. So this triangle ABC that could be any triangle according to the law of cosines, the following equation is 2. C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So the first step, we will implement the law of cosines. This great triangle BAD. So according to the law of cosines, it is great triangle ABD. The following equation will be 2. BD squared equals to AD squared plus AB squared minus 2 times AD times AB times cosine 180 degrees minus alpha. Repeat again, according to the law of cosines, in this rectangle BD, the following equation is 2. BD squared equals to AD squared plus AB squared minus 2 times AD times AB times cosine 180 degrees minus alpha. And again, this great triangle ABD according to the law of cosines, the following equation is 2. BD squared equals to AD squared plus AB squared minus 2 times AB times cosine 180 degrees minus alpha. We have the trigonometric identity that states that cosine 180 degrees minus alpha equals to minus cosine alpha. So according to this trigonometric identity, we get that cosine 180 degrees in this equation 1 equals to minus cosine alpha. So in total we have here, according to equation 1, we have BD squared equals to AD squared. AD is 6, therefore AD squared is 6 squared, that is 36, plus AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, minus 2 times AD is 6, times AB, that is 3, times cosine 180 degrees minus alpha. And cosine 180 degrees minus alpha equals to minus cosine alpha according to this trigonometric identity. So in total, this equation we have minus times minus, that is plus. So this expression, in the green color, it is a positive expression. So in total, we found out that BD squared, according to equation 1, BD squared equals to 36 plus 9 is 45. Here minus times minus is plus, so it is plus. 2 times 6 is 12. 12 times 3 is 36. So total this expression equals to 36 cosine alpha. So total according to equation 1, we found out that BD squared equals to 45 plus 36 times cosine alpha. This is according to equation 1. So in the next step, we will implement the law of cosines in this lower triangle BDC. So according to the law of cosines, in this lower triangle BDC, we get that BD squared equals to DC squared plus BC squared minus 2 times CD times BC times cosine alpha. And again, in this lower triangle BDC, according to the law of cosine, the following equation is 2. BD squared equals to CD squared plus BC squared minus 2 times CD times BC times cosine alpha. And according to equation 1, we already found out that BD squared equals to 45 plus 36 cosine alpha. So we have two different equations for the value of BD squared. Therefore, we get equation 3 that says that BD squared according to equation 1 must be equal to BD squared according to equation 2. Very simple equation. BD square according to equation 1 equals to 45 plus 36 times cosine alpha. And what we equal to BD square according to equation 2. BD square according to equation 2 equals to CD square plus BC square minus 2 times CD times BC times cosine alpha. So first of all, we find out the value of the equation 2. We complete the value of equation 2. We get that according to equation 2, BD square equals to CD square. CD is 5, therefore CD square is 5 squared, that is 25, plus BC square. BC is 4, therefore BC square is 4 squared, it is 16, minus 2 times CD, that is 5, times BC, that is 4, times cosine alpha. So total according to equation 2, we found out that BD square equals to 25 plus 16 is 41. Here we have minus 2 times 5 is minus 10, minus 10 times 4 is minus 40, times cosine alpha. So total according to equation 2, we found out that BD square equals to 41 minus 40 times cosine alpha. This is according to equation 2, while according to equation 1, we already found out that BD square equals to 45 plus 36 cosine alpha. Therefore, we get equation 1, equation 3 that says that BD square according to equation 1 must be equal to BD square according to equation 2. So I copy this equation here, new page. Okay, again, equation 3 says that BD square according to equation 1 must be equal to BD square according to equation 2. Very simple equation. BD square according to equation 1 equals to 45 plus 36 times cosine alpha. And it must be equal to BD square according to equation 2. BD square according to equation 2 equals to 41 minus 40 times cosine alpha. So according to equation 3, we found out that BD square, according to equation 3, we found out that 45 plus 36 cosine alpha equals to 41 minus 40 times cosine alpha. So here we subtract 41 from this equation 3. Again, according to equation 3, here 41 will get cancelled, and therefore with minus 40 times cosine alpha on this side of the equation 3, and on the other side of equation 3 we have 45 minus 41 is 4 plus 36 times cosine alpha. So total according to equation 3, if you found out that 45, that 4 plus 36 cosine alpha equals to 40 times cosine alpha, minus 40 times cosine alpha. So here we add add 40 times cosine alpha to this equation. So here minus 40 times cosine alpha we get cancelled, and you have to be nothing, that is to say 0 on this side of equation 3. While on the other side of equation 3 we have 40 times cosine alpha plus 36 times cosine alpha is equal to 76 times cosine alpha plus 4. So in total, according to equation 3, we should find out that 4 plus 76 cosine alpha equals to 0. So here we subtract 4 from this equation 3. We get according to equation 3, 4 will get cancelled. So inside of equation 3, we left only with 76 times cosine alpha, and on the other side of equation 3, 0 minus 4 is minus 4. So in total, according to equation 3, we found out that 76 times cosine alpha equals to minus 4. Here we divide this equation 3 by 76, and finally get according to equation 3, cosine alpha equals to minus 4 over 76. According to equation 3, cosine alpha equals to minus 4 over 76. Minus 4 over 36 equals to minus 0.0526. So those two sides of the equation are equal to each other. So in total, we found out that according to equation 3, cosine alpha equals to minus 0.0526. And again, according to equation 3, we found out that cosine alpha equals to minus 0.0526. We would like to find the value of alpha itself. In order to find the value of alpha itself, we will have to operate the opposite function of cosine, the inverse function of cosine on the result of cosine alpha. This is actually minus 0.0526. In this way, we get the value of alpha itself. So the inverse function of cosine alpha, operate the inverse function of cosine alpha on the result of cosine alpha. This is actually minus 0.0526, and the value of this expression will be equal to alpha. So the inverse function of cosine on minus 0.526 will give us that alpha equals to 93.017 degrees in its size. And again, if we found out that this is the missing angle alpha, that is equal to 93.107 degrees in its size. As you know, alpha equals to 93.1.017 degrees in its size. In the next step, we will implement the law of sines in this lower triangle BDC. We implement the law of sines in this full version of this lower triangle BDC. But before that, we'll have to find out the value of dB itself. According to equation 2, we already found out that dB squared equals to 41 or 40 times cosine alpha. Okay, copy equation 2 on a new page. According to equation 2, we already found out that BD squared equals to 41 minus 40 times cosine alpha. So BD squared equals to 41 plus, minus 40 times cosine alpha. Alpha equals to 93.017 degrees inside. So alpha equals to 93.017 degrees inside. So in total, we should know that according to equation 2, BD squared equals to 41 minus 40 times cosine 93 degrees, 0.017. The value of this expression in the green color in total is equal to 2.105. So it is plus 2.105. So in total we found out that BD squared equals to 41 plus 2.105. So BD squared, according to equation 2, BD squared equals to 41 plus 2.105 is 43.105. Here we take out all those equations, and get that BD, the left of side BD is equal to the square root of 43.105. The square root of 43.105 is equal to 6.565 units in Israel. And again, to that we should find out that the left of side BD is equal to 6.565 units in Israel. In the next step, we will implement the law of sines. This law of triangle BDC. So please click on the law of sines. This is triangle ABC that could be any triangle. Triangle ABC is described by this circle. The radius of this circle is R. This is angle BAC is equal to capital A degrees inside. This is angle BC is equal to capital B degrees inside. This is angle ACB is equal to capital C degrees inside. Side AB, this triangle ABC is equal to C units in itself. Side AC equals to B units in itself. And finally, side BC of this triangle ABC is equal to A units in itself. So according to the law of sines in its full version, in this our drawing, the following equation is to A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R. And now with the radius of this circle, that's both triangle ABC. But again, according to the law of sines in its full version, our drawing, the following equation is to A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R. And again, now the radius of this circle, that's both triangle ABC. The triangle ABC is described by this circle. So we can implement the law of sines in its version in our drawing. First of all, it is very clear from the drawing that the lower triangle BDC is described by this circle. Why? Because of the fact that all the three vertices this triangle BDC, this is actually B, C, and D, lie in the circle itself. Therefore, triangle BDC is described by this circle. For that reason, we can implement the law of sines in its full version, this triangle BDC. So according to the law of sines, its full version. In this non-trial BDC, the following equation is true. dB over sinus alpha equals to 2R. Again, BD over sinus alpha equals to 2R. And now, if the radius of this circle, that is the radius that we are looking for in this question. So, according to the law of sines, in the non-trial BDC, the following equation is true. BD over sinus alpha equals to 2R, and R is the radius of the circle that we are looking for. We already found out that BD equals to 6.565 units in Islam. Over sinus alpha. We already found out that alpha equals to 95.017 degrees in size. So BD over sinus alpha equals to 2R. So now we found out that BD equals to 6.565 and sinus alpha is sinus 93.1017 degrees. In total we found out that 6.565 over sinus 93.017 equals to 2R. Actually, the value of this expression in the green color, in total it is equal to 6.5745. Those two sides of the equation are equal to each other. That is to say 6.5745 equals to 2R. Here we divide this equation by 2 and we get that the radius R, that is the radius that we are looking for this question, equals to 6.575 over 2, is equal to 3.287 units in its length. And again, to that, we found out that the radius of this circle, that is the radius that we are looking for this question, is equal to 3.287 units in its length. So we finished to answer on the first question. The next step, I'll present to the second question and answer the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have the big quadrilateral ABCD. We know that AP equals to PB. Side BC of this quadrilateral, of this big quadrilateral ABCD equals to 7 units in its length. Side AD equals to 9 units in its length. Side DC equals to 8 units in its length. Those three angles are all right angles. Again, our task is to find out the area of this green shape. So first of all, AB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. So if we focus on the lower side of the straight line AB at point P, here the sum of the angles must be equal to 180 degrees according to rule 3. all three sides, that's the sum of the angles on one side of the side line is equal to 180 degrees. So which angles we have at the lower side of the side line AB at point B? We have this angle, that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. The next step, we will join points A and Q together by a straight line. Likewise, we will join points B and Q together by a straight line. By doing this, those constructions, we can deduce two right triangles. This is the white triangle, the white right triangle APQ, and this is the white green triangle, the right green triangle BPQ. So the next step, we will prove that those two triangles can go into each other according to side against side rule. And again, we prove that those two white triangles, that is to say the white triangle and the green triangle, can go into each other according to side against side rule. So we have to prove that this is the white right triangle APQ. That this right triangle APQ can go to this green right triangle PBQ. So why those two right triangles can go into each other? First of all, AP equals to PB according to what is given as the question. And again, side AP of the white triangle equals to side PB of the green triangle according to what is given as the question. In addition, those two angles are both right angles and therefore they are equal to each other. So actually this angle APQ, the white triangle, is equal to this angle BPQ, the green triangle. And again, if you want to know that angle APQ in the white triangle equals to angle BPQ in the green triangle, they are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side PQ, this is a common side that belongs to both triangles. So we can write down that PQ equals to itself is a common side that belongs to both triangles. So in total, we have found out that those two triangles can go into each other according to side against side rules. So that is all. We have found out that the white triangle APQ congruent, this is the sign of congruent, to the green triangle PBQ according to side against side rule. That is to say, we have found out that those two sides and the angle that is included between those two sides in this right triangle are corresponding equal to those two sides and the angle that is included between those two sides in this green triangle. Therefore, those two right triangles can go to each other according to side angle side rule. Repeat again. We have those two sides and the angle that is included between those two sides in this right triangle are corresponding equal to those two sides and the angle that is included between those two sides in this green triangle. And therefore, those two right triangles can go into each other according to side angle side rule. And for the fact that those two right triangles can go into each other, we will derive two things. The first thing that we will derive that the areas of those two congruent triangles must be equal to each other in their sizes. That is to say, the area of this right triangle APQ is equal to the area of this green triangle PBQ. And again, from the fact that those two right triangles can go into each other, we will have that they have also the same areas. That is to say, the area of the white triangle PQ equals to the area of the green triangle PPQ. So if we define the area of the green triangle PBQ as A, then the area of the triangle PQ must be also equal to A because they are equal to each other in their areas. So we define the area of this right triangle APQ as A, that is to say, it is equal to A squared inside according to our definition. And because of the fact that the area of those two right triangles are equal to each other, the area of this green triangle PBQ must be also equal to A squared in its size. The second thing that we will derive from the fact that those two right triangles can go into each other, we derive that AQ equals to QB. Side AQ of the white triangle is equal to side PB of the green, to side BQ of the green triangle. Why AQ equals to BQ? AQ equals to BQ according to the rule that says that corresponding sides and congruent triangles can go to each other. Those two triangles can go into each other, therefore their corresponding sides, that is to say AQ and BQ, must be also equal to each other in their lengths. So, therefore AQ equals to BQ. In the next step, we will square this equation, equation 2. Get that, according to the equation, get that AQ square equals to BQ square. Here we can implement Pader's theorem. According to the Pader's theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle ADQ, the square of the hypotenuse is AQ square, and AQ square must be equal to AD square plus DQ square. Therefore, we can substitute AQ square in this equation 2 by AD square plus DQ square. This is all according to the Pader's theorem. And AQ square equals to BQ square. In this green triangle BQC, according to the Pader's theorem, according to the Pader's theorem, BQ square, that is the square of the hypotenuse, must be equal to BC square plus CQ square. Therefore, we can substitute BQ square by BC square plus CQ square. Here we substitute BQ square in this equation. Equation 2 by BC square plus QC square. In total, according to equation 2, actually found out that AD square plus DQ square equals to BC square plus QC square. AD is 9, therefore this square is 9 squared, that is 81, plus DQ square. We find the length of DQ as x. What is the length of QC? From the domain, it is very easy to see that QC in total equals to DC minus DQ. Again, QC equals to DC minus DQ. So QC equals to DC minus DQ. So QC in total equals to DC. DC equals to 8 units in its length according to what is given as the question, minus DQ. DQ equals to X according to our definition. So in total we found out that QC equals to 8 minus X units in its length. QC, that means inside QC equals to 8 minus X units in its length. What is the definition of the big quadrilateral ABCD? Actually, those two right angles are defined as one-sided antiangles. The sum of those two right angles is of course 180 degrees, and because of the fact that the sum of those two one-sided antiangles is equal to 180 degrees, they must be located between parallel lines. That is to say, AD is parallel to BC, according to Rule 20. So if it's quickly on Rule 20, according to Rule 20, if the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. So in the drawing we have line A, this is line A, this is line B, this is the transversal C, the transversal C that cuts those two lines and those 2 points. Those two angles, alpha and beta, they are defined as one-sided interangles. So if the sum of those two angles is equal to 180 degrees, that is to say, if alpha plus beta equals to 180 degrees, then they must be located between parallel lines. That is to say, line A is parallel to line B. So if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Likewise, those two angles, gamma and delta, are both defined as one-sided interangles. So if the sum of those two one-sided interangles is equal to 180 degrees, that is to say, if gamma plus delta equals to 180 degrees, then they must be located between parallel lines. That is to say, line A is parallel to line B. We already implemented Rule 20 in our drawing. Because in our drawing, the sum of those two one-sided triangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AD is parallel to BC. So in the big quadrilateral ABCD, AD is parallel to BC. And because of the fact that the big quadrilateral ABCD has one pair of parallel sides, that is to say, AD is parallel to BC, quadrilateral ABCD is defined as a trapezoid. Because a trapezoid is a quadrilateral with one pair of parallel sides. So in total, we found out that quadrilateral ABCD is a trapezoid. So it is known, the big quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. What is the area of a trapezoid? This is trapezoid ABCD. Side AB is parallel to side CD. So those two parallel sides are defined as the bases of this trapezoid. So the area of a trapezoid equals to the sum of its two parallel bases. So if AB equals to A and BC equals to A, then the sum of the two parallel bases is A plus B times the right edge over 2. The right edge must create 90 degrees with the two parallel bases. This is right angle. This is also right angle. So the area of a trapezoid equals to the sum of its two parallel bases. That's actually A plus B times the right edge over 2. So we implement the new rule in order to find out the area of our trapezoid ABCD. So the area of this big trapezoid ABCD must be equal to the sum of its two parallel lines, that is to say it is AD plus BC times the height DC over 2. DC is the height because of the fact that it gets integrated with those two bases. So in total we found out that the area of the big trapezoid ABCD equals to AD plus BC times CD over 2. The area of trapezoid ABCD in total is equal to the sum of its two parallel bases, is actually AD plus BC times the height H. H is DC, because it's 90 degrees with those two parallel bases, those two angles are right angles. The height is DC over 2. And again, in total, we found out that the area of this big trapezoid ABCD is equal to AD plus BC, that is the sum of its two parallel bases, times the height DC over 2. AD equals to 9 plus BC equals to 7 times DC equals to 8 over 2. So in total we found out that the area of the big trapezoid ABCD equals to 9 plus 7 times 8 over 2. 9 plus 7 is 16, 8 over 2 is 4. So in total this expression equals to 16 times 4. 16 times 4 is 64. So in total we found out that the area of the big trapezoid ABCD equals to 64 square units in its size. So, according to the first method of calculation, the area of trapezoid ABCD equals to 64 square units in size. We can find out the area of this trapezoid ABCD in a different way. It's very clear that the area of trapezoid ABCD must be equal to the sum of the rest of the four components that it consists of. That is to say, it is the area of this first component plus the area of this second component plus the area of this third component plus the area of this fourth component. Okay, so it is on. In total, according to the second method of calculation, we actually found out that the area of this trapezoid ABCD is equal to of the first component that trapezoid ABCD consists of, that's actually this right angle ADQ plus the area of the second component that trapezoid ABCD consists of, that's actually the area of this right angle APQ plus the area of the third component the trapezoid ABCD consists of, the area of this right angle PBQ plus the area of the fourth component the trapezoid ABCD consists of, the area of this right angle BQC. So in total, we found out that the area of the big trapezoid ABCD is equal to the sum of the rest of those four components that trapezoid ABCD consists of. So we calculate the area of each component separately, and then we let the four areas together. Of course, will be the area of trapezoid ABCD according to the second method of calculation. So first of all, we find out the area of the first component that trapezoid ABCD consists of. So it's actually the area of the right angle ADQ. This is the area of this right angle ADQ. It's very easy to say from the drawing that the right angle ADQ equals to dq times dA over 2. Okay, it is dq times dA over 2. dq times the height dA over 2. But before that, we have to find out the value of dq equals to x. We already found out that aq equals to bq because of the fact that those sides can go into each other. Therefore, their corresponding sides must transfer to each other and their lengths. That is to say, aq equals to bq. Then let's square this equation and find out that aq squared equals to bq squared. aq squared is ad squared plus dq squared, and bq squared equals to bc squared plus qc squared according to the Pythagoras theorem. AD is 9, therefore d squared is 9 squared, that is 81 plus dq squared. dq is x, therefore dq squared is x squared. And is equals to bc squared. bc is 7, therefore bc squared is 7 squared, that is 49. Plus qc squared. qc is 8 minus x, therefore qc squared is 8 minus x squared. So in total, we should find out that according to equation 2, 81 plus x squared equals to 49 plus 8 minus x squared. So according to equation 2, we should find out that 81 plus x squared equals to 49 plus 8 minus x squared. According to the algebraic identity, that says that a minus b squared equals to a squared plus b squared minus 2 times a times b. We get that the value of this expression, 8 minus x squared equals to 8 squared, that is 64, plus x squared minus 2 times 8 times x, that is minus 16x. Here we have x squared on both sides of this equation, so x squared get cancelled. Not take x squared, this side of the equation we have only with 81, while on the other side of the equation we have 49 plus 64 is 113 minus 16x. So total according to equation 2, if you want to know that 81 equals to 113 minus 16x. Here we add 16x to this equation 2, and we found out that equation, according to equation 2, 16x plus 81 equals to 113. Here we subtract 81 from this equation 2, and finally get that according to equation 2, here 81 gets cancelled, and left only 16x. And on the other side of the equation we have 113 plus 81 is 32. So in total we should find out that 16x equals to 32. Here we divide this equation by 16. And you get that x equals to 32 over 16 is 2. In total, we should find out that x equals to 2 units in its length. This is 9 times dq equals to x, and x equals to 2. Likewise, this equals to 8 minus x. 8 minus x is 8 minus 2. 8 minus 2 is 6. So in total, qc equals to 6 and dq equals to 2. Therefore, the area of the first component that quadrilateral ABCD consists of is the area of this right triangle ADQ. The area of this right triangle ADQ equals to the base that is 2 times the height that is 9 over 2. 2 times 9 over 2 is 9. So the area of the first component that quadrilateral ABCD consists of is equal to 9 square units in size. So until now, in total, I should found out that the area of the big trapezoid ABCD equals to the sum of the earth of those four components that it consists of. They have the first component, it is the area of this right triangle AD cube. We found out that the area of this right triangle AD cube equals to 9 square units in size. So the area of the first component is equal to 9 square units in size, plus the area of the second component. The area of the second component is equal to 8 square units in size according to our definition. So it is A plus the area of the third component that trapezoid ABCD consists of, the area of this again Q BPQ is also equal to 8 square units in size. So the first component is also A square units in size plus the area of the fourth component that trapezoid ABCD consists of. The fourth component is actually the area of this green triangle QCB. The area of the green triangle QBC equals to the base QC, that is 6, times the height CB, that is 7 over 2. 6 times 7 is 42, and 42 over 2 is 21. So total the area of the fourth component that the ABCD consists of is 21 square units in size. Okay, again, the area of the first component that the ABCD consists of is equal to 21 square units in size. So total the value of this expression is the total area of trapezoid ABCD. The value of this expression equals to 9 plus 21 is 30, 8 plus 8 is 2a. So according to the second method of calculation, the area of the big trapezoid ABCD is equal to 30 plus 2a square units in size. Again, the area of the big trapezoid ABCD, according to the second method of calculation, is equal to 30 plus 2a square units in size. And we already found out that according to the first method of calculation, the area of the same trapezoid ABCD is equal to 16 square units in size. And again, according to the first method of calculation, the area of the same trapezoid ABCD is equal to 16 square units in size. So we have the area of trapezoid ABCD in both those two equations. Therefore, equation 1 and equation 2, therefore we get the equation 3 that says that the area of trapezoid ABCD according to the first method of calculation must be equal to the area of the same trapezoid ABCD according to the second method of calculation. Very simple equation. And again, equation 3 states that the area of the big trapezoid ABCD according to the first method of calculation must be equal to the area of the same trapezoid ABCD according to the second method of calculation. Very simple equation. According to the first method of calculation, the area of trapezoid ABCD equals to 16 square units in size. It must be equal to the area of the same trapezoid ABCD according to the second method of calculation. According to the second method of calculation, the area of the same trapezoid ABCD is equal to 30 plus 2a squared in size. So total according to equation 3, we should find out that 16 equals to 30 plus 2a. Here we subtract 16 equals to 30, it is actually 64. Made a mistake here. The area of the big trapezoid ABCD according to the first method of calculation equals to 64 squared in size. So it is not 16 but 64. So in total we found out that 64 equals to 30 plus 2a. Here we subtract 30 from this equation 3. Get that according to equation 3, here 30 will get cancelled, and we have only 2a this side of the equation, and on the other side of the equation we have 64 plus 30 is 34. So in total according to equation 3 we found out that 34 equals to 2a. Here we divide this equation 3 by 2, and finally get that according to equation 3, a equals to 34 over 2. 34 over 2 is 17. So in total we found out that a equals to 17 is correct in size. And again, we found out that this is that quintile PBQ. There this quintile ABQ equals to a squared inside. That is to say, it is equals to 16 squared in 17 squared inside. Likewise, they have this right quintile PBQ also equals to a, and a equals to 17 squared inside. What is the of the green shape? The of the green shape equals to they have this green tile PBQ, that is to say a and a is 17, plus they have this green tile PBCQ, that is actually 21. So in total, the area of the green shape equals to 17 plus 21, that is 38. Okay, now they have the big one, they have the green shape, that is the area that we're looking for in this question. In total, it is equal to 17 plus 21 is actually 38 correct in size. And again, total we found out that the area of this green shape, that is the area that we're looking for this question, is equal to 38 correct in size. So we finish the rest of the second question. In the next step of the lecture, this is to say, we repeat on the solution of the first question, and then we repeat on the solution of this second question. In the first question, our task is to find out the radius of this circle. So in the drawing, we have quadrilateral ABCD that is described by this circle. Side AD of quadrilateral ABCD equals to 6 units in its length, side AB equals to 4 units in its length, side BC equals to 4 units in its length, and finally side DC equals to 5 units in its length. Again, our task is to find out the radius of this circle that blocks this quadrilateral ABCD. So first of all, we define this angle BCD as alpha. Therefore, the opposite angle BCD, angle BAD, this is the opposite angle of this angle. This angle must be equal to 180 degrees minus alpha. Why? Because 180 degrees minus alpha plus alpha is equal to 180 degrees. This is the sum of those two opposite angles inside cyclic quadrilateral ABCD. So we have the rule that says that the sum of the opposite angles in any cyclic quadrilateral is equal to 180 degrees. This is the cyclic quadrilateral ABCD. Because of the fact that ABCD is a cyclic quadrilateral, the cyclic quadrilateral ABCD is described by this blue circle. And therefore, the sum of those two angles is equal to those two opposite angles is equal to 180 degrees. That is to say, x plus y equals to 180 degrees. Likewise, the sum of those two opposite angles inside quadrilateral ABCD, inside the cyclic quadrilateral ABCD, must be equal to 180 degrees. That is to say, a plus b also equals to 180 degrees. We already implemented this new rule in our drawing. Well, because in our drawing, quadrilateral ABCD is of course a cyclic quadrilateral. Therefore, inside the cyclic quadrilateral ABCD, the sum of those two opposite angles must be equal to 180 degrees. But this angle is alpha according to our definition. Therefore, this base angle must be equal to 180 degrees minus alpha. Again, why? Because 180 degrees minus alpha is equal to 180 degrees. It is the sum of those two opposite angles inside the cyclic quadrilateral ABCD. Therefore, this base angle must be equal to 180 degrees minus alpha. The next step, we join points B and D together by straight line. By joining points B and D, we divided quadrilateral ABCD into two parts. The first part is the green triangle ABD. The second part is the white triangle BDC. So in the next step, we implemented the law of proportions on both triangles. So first of all, we implemented the law of cosines, this green triangle BAD. So we pinch quickly on the law of cosines. The law of cosines is drawn in any triangle, so this is triangle ABC that could be any triangle. This angle BAC, this angle BAC is equal to theta divided inside. Side AB equals to A in its left, side AC equals to B in its left, side BC equals to C in its left. So in this triangle ABC that could be any triangle according to the law of cosines, the following equation is 2. C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So in the first step, we implemented the law of cosines, this green triangle ABD. According to the law of cosines, in this green triangle ABD, the following equation is 2. BD squared equals to AD squared plus AB squared minus 2 times AD times AB times cosine 180 degrees minus alpha. Again, according to the law of cosines, this green triangle BD, the following equation is 2. BD squared equals to AD squared plus AB squared minus 2 times AD times AB times 180 degrees minus alpha. We have the trigonometric identity that says that cosine 180 degrees minus alpha equals to minus cosine alpha. Therefore, we can substitute cosine 180 degrees in this equation 1 by minus cosine alpha. And we have also BD squared equals to AD squared. AD 6, therefore AD squared is 6 squared, plus AB squared. AB is 3, therefore AB squared is 3 squared, this is 9. AD squared equals to 36, plus AB squared equals to 9. We have minus 2 times AD, that is 6, times AB, that is 3, times cosine 180 degrees minus alpha. According to this trigonometric identity, cosine 180 degrees minus alpha equals to minus cosine alpha. So in total, according to equation 1, which we found out that BD squared equals to 36 plus 9, minus 2 times 6, minus 2 times 6 times 3, times minus cosine alpha. Minus times minus is plus, so this expression in the green color is a positive expression. The value of this positive expression is plus 2 times 6 is 12, 12 times 3 is 36, and total the value of this expression is equal to plus 36 times cosine alpha, and 36 plus 9 is 45. So in total, we found out that according to equation 1, BD squared equals to 45 plus 36 times cosine alpha. Likewise, we implemented the law of cosines in this lower triangle BDC. According to the law of cosines, this lower triangle BDC, the following equation is 2. BD squared equals to DC squared plus BC squared minus 2 times DC times BC times cosine alpha. And again, this lower triangle BDC, according to the law of cosines, the following equation is 2. BD squared equals to CD squared plus BC squared minus 2 times CD times BC times cosine alpha. We continue to develop this second equation. We get that BD squared equals to CD squared. CD is 5, therefore CD squared is 5 squared, this is 25, plus BC squared. BC is 4, therefore BC squared is 4 squared, this is 16. Again, CD squared equals to 25, BC squared equals to 16, minus 2 times CD, that is 5, times BC, that is 4 times cosine alpha. So in total, we found out that BD squared equals to 25 plus 16, that is 41. Minus 2 times 5 is minus 10. Minus 10 times 4 is minus 40. So in total, this expression equals to minus 40 times cosine alpha. So in total, according to equation 2, we found out that BD squared equals to 41 minus 40 times cosine alpha. Well, according to equation 1, we found out that BD squared equals to 45 plus 36 times cosine alpha. So we have two different equations for BD squared. Equation 1 and equation 2. Therefore, we get the equation 3 that says that BD squared according to equation 1 must be equal to BD squared according to equation 2. Very simple equation. Again, we get the equation 3 that says that BD squared according to equation 1 must be equal to BD squared according to equation 2. BD squared according to equation 1 equals to 45 plus 36 times cosine alpha, and must be equal to BD squared according to equation 2. BD squared according to equation 2 equals to 41 minus 40 times cosine alpha. So in total, according to equation 3, we should find out that 45 plus 36 times cosine alpha equals to 41 minus 40 times cosine alpha. So here we subtracted from this equation 3, 41, so 45 minus 41 is 4, plus 36 cosine alpha, here 41 will get cancelled, we left only with minus 40 times cosine alpha. So total according to equation 3, we found out that 4 plus 36 cosine alpha equals to minus 40 times cosine alpha. So we added here 40 times cosine alpha to this equation 3. So here minus 40 times cosine alpha will be cancelled. Left with nothing, that is to say 0. But on the other side of the equation, we have 40 times cosine alpha plus 36 times cosine alpha is 76 cosine alpha. So in total, this expression equals to 4 plus 76 cosine alpha equals to 0. If subtracted 4 from this equation 3, we found out that according to equation 3, here 4 we get cancelled. Left only with 76 cosine alpha equals to 0 minus 4 is minus 4. So in total, according to equation 3, we found out that 76 cosine alpha equals to minus 4. Here we divided the equation 3 by 76, and finally found out that cosine alpha equals to minus 4 over 76. Minus 4 over 76 equals to minus 0.0526. So those two sides of the equation are equal to each other. This is to say cosine alpha equals to minus 0.0526. We would like to find out the value of alpha itself. In order to find out the value of alpha itself in this equation 3, we operate the opposite function of cosine, the inverse cosine of the result of cosine alpha, this is actually minus 0.0526. In this way, we get the value of alpha itself. So the inverse cosine, the opposite function of cosine, if we operate it on the result of cosine alpha, this is actually minus 0.0526, we get the value of alpha itself. We can find out in any simple scientific calculator that the value of this expression equals to 93.017 degrees. So in total, we should find out that alpha equals to 93.017 degrees in size. So okay, this is angle alpha, equals to 93.017 degrees in size. The next step, we found out the value of BD. According to equation 2, we only found out that BD squared equals to 41 minus 40 times cosine alpha. So BD squared equals to 41 minus 40 times cosine alpha. Alpha is 93.017. So in total, according to equation 2, we found out that BD squared equals to 41 minus 40 times cosine 93.017 degrees. The value of this expression, so that is equals to 2.105. So total according to equation 2, we found out that BD squared equals to 41 plus 2.105. 41 plus 2.105 equals to 43.105. So total according to equation 2, we found out that BD squared equals to 43.105. Here we took a root out of this equation. And finally found out that BD equals to the square root of 43.105, that is actually 6.565 units in its length. This is side BD. Is equal to 6.565 units in its length. The next step, we implemented the law of sines in its full version, and this lower triangle BDC. So repeat quickly on the law of sines in its full version. In the drawing, we have triangle ABC that is described by this circle. The radius of this circle is R. This angle BAC is equal to capital A divided in size. This angle ABC is equal to capital B divided in size. And finally, this angle ACB is equal to capital C divided in size. Likewise, side AB with this side ABC equals to 3 units in length, side BC equals to 1 unit in length, side AC equals to B units in length. So in our drawing, according to the law of sines in its full version, the following equation is to A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R. And R is the radius of this circle that draws triangle ABC. Repeat again, according to the law of sines in its full version, the following equation is to A over sinus A equals to B over sinus B equals to C over sinus C equals to 2R. Again, R is the radius of this circle that draws triangle ABC, or triangle ABC is described by this circle. So we can definitely implement the law of sines in its full version in our drawing. Triangle DBC is described by this circle. Why triangle DBC is described by this circle? Because of the fact that all of its three vertices, that is to say D, B, and C, lie in the circle itself. Therefore, because of the fact that triangle DBC is described by this circle, we can implement the law of sines in full version, this triangle DBC. According to the law of sines in full version, this triangle DBC, the following equation is to dB over sinus alpha equals to 2R. And now the radius of this circle that draws triangle DBC. Again, according to the law of sines in full version, this triangle BDC, the following equation is to BD over sinus alpha equals to 2R. And now the radius of the circle that we are looking for. And again, the triangle BDC, according to the law of sines in full version, BD over sinus alpha equals to 2R. And now is the radius of the circle that we are looking for. BD equals to 6.565 and alpha equals to 93.017 degrees in size. Again, BD is 6.565 and sinus alpha is 93.017 degrees. Equals to 2R. The value of this expression in total is equals to 6.5745. So those two sides of the equation are equal to each other. That is to say 6.5475 equals to 2R. If we divided the equation by 2 and finally found out that R, that is the radius of the circle that we are looking for, is equal to 3.287 units in its length. The radius of this circle R equals to 3.287 units in its length. So we finished to answer the first question. We finished to repeat the solution of the first question. In the next step, I repeat the solution of the second question. The second question, our task is to find out the area of this green shape. So in the drawing, we have the big quadrilateral ABCD. AB equals to PB. Side AD of this big quadrilateral ABCD equals to 9 units in length. Side DC equals to 8 units in length. And finally, side BC equals to 7 units in length. Those three angles are all right angles. Again, our task is to find out the area of this green shape. So first of all, AB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. So if you focus on the lower side of the straight line AB at point P, here the sum of the angles must be equal to 180 degrees in its side. So which angles we have at the lower side of the straight line AB at point P? We have this angle, this is right angle, plus this 3 circles. In total, the sum of those two angles must be equal to 180 degrees according to all three. All three said that the sum of the angles on one side of the third line is equal to 180 degrees. So the sum of those two angles must be equal to 180 degrees. Therefore, this 3 circle must be equal to 9 degrees inside. And again, this 3 circle must be equal to 9 degrees inside. In the next step, we join points A and Q together by side line. Likewise, we join points B and Q together by side line. By doing those constructions, we get those two white triangles. The white triangle EPQ and the green white triangle PQ. So the next step, we prove that those two white triangles can go into each other according to side angle side rule. So those two white triangles can go into each other. First of all, AP equals to PB according to what is given as the question. In addition, those two angles are both right angles and therefore they are equal to each other. And finally, PQ is a common side that belongs to both angles, so we can write down that PQ equals to itself is a common side that belongs to both angles. So in total, we found out that the white triangle PQ can go to the green triangle PBQ according to angle side angle rule. And in total, we found out that the white triangle PQ can go, this is the sum can go to the green triangle PQ according to side against side rule. This is to say, we found out that those two sides and the angle that is included between those two sides in this white triangle are corresponding equal to those two sides and the angle that is included between those two sides in this green triangle. Therefore, those two white triangles can go into each other according to side against side rule. And from the fact that those two white triangles can go into each other, we derive two things. The first thing that we derive that they have also the same areas. That is to say, the area of the white triangle PQ equals to the area of the green triangle PBQ. And two triangles that can go into each other have also the same areas. So if we define the area of the green triangle is A, then the area of the white triangle must be also equal to A because they are equal to each other in their sizes. So if the area of the green triangle is A, then the area of the white triangle PQ must be also equal to A because they have the same areas. The first thing that we will derive that from the fact that those two white triangles can go into each other, we know that their corresponding sides must be also equal to each other and their lengths. That is to say, AQ equals to QB. Okay. And again, AQ equals to QB according to the rule that said that corresponding sides and white triangles are equal to each other. Those two triangles can go into each other, therefore their corresponding sides, that is to say AQ and BQ must be also equal to each other and their lengths. So AQ equals to QB. Here we squared both sides of this equation and found out that AQ squared equals to BQ squared. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So what is the value for AQ squared? If we focus on this right triangle AD is Q, the hypotenuse is AQ. So according to the Pythagoras theorem, this right triangle ADQ, AQ squared, that is the square of the hypotenuse, must be equal to AD squared plus DQ squared. So in total, AQ squared equals to AD squared plus DQ squared. Again, according to the Pythagoras theorem, we found out that AQ squared equals to AD squared plus DQ squared. Therefore, we substitute AQ squared in this equation 2 by AD squared plus DQ squared. Likewise, what is the value of BQ squared? This green right triangle BQC, according to the Pythagoras theorem, BQ squared, that is the square of the hypotenuse, must be equal to BC squared plus CQ squared. Therefore, BQ squared equals to BC squared plus CQ squared. And again, according to the Pythagoras theorem, BQ squared equals to BC squared plus CQ squared. So therefore, substitute BQ squared in this equation 2 by BC squared plus CQ squared. So total, according to equation 2, we found out that AD squared plus DQ squared equals to BC squared plus Q squared. AD is 9, therefore this square is 9 squared, that is 81. Plus DQ squared. We define DQ as x, therefore DQ squared is x squared, and it equals to BC squared. BC is 7, therefore BC squared is 7 squared, that is 49. What is the value of QC? in total QC must be equal to DC minus DQ. Again, QC must be equal to DC minus DQ. DC is 8 according to this equation, DQ is X according to our definition. So in total QC equals to 8 minus X. If QC equals to 8 minus X, it means that QC square must be equal to 8 minus X square. And again, QC square equals to 8 minus X square. So in total, according to equation 2, if you found out that 81 plus X square equals to 49 plus 8 minus X square. So we have 81 plus X square equals to 49 plus 8 minus X square. 8 minus X square equals to 8 square, that is 64, plus X square, minus 2 times 8 times X, that is minus 16. Here we have X square on both sides of this equation, so X square we cancelled. After cancelled X square, this side of the equation we left only with 81, while on the other side of the equation we left with 49 plus 64, this is out as 13, minus 16x. So total we found out that 81 equals to 113 minus 16x. Here we added 16x to this equation, so here 16x will get cancelled, and we left only with 113 on this side of the equation, while on the other side of the equation we have 81 plus 16x. So total according to the equation 2, we found out that 81 plus 16x equals to 113. Here we subtracted 81 from this equation, equation 2. So here 81 will get cancelled, and we left only with 16x. While on the other side of the equation we have 113 minus 81 is 32. So in total according to equation 2, we actually found out that 16x equals to 32. Here we divided this equation by 16, and we found out that x equals to 32 over 16 is 2. So x equals to 2 units instead. This is 97 dq is equals to x, and x equals to 2, therefore dq equals to 2. Likewise, qc equals to 8 minus x. 8 minus x is 8 minus 2, that is 6. So in total qc equals to 6. What is the definition of quadrilateral ABCD? Because of the fact that the sum of those two one-sided triangles is equal to 180 degrees, those two angles must be located between parallels. That is to say, AD is parallel to BC, according to Rule 20. So repeat quickly Rule 20. According to Rule 20, if the sum of two triangles, one-sided angles is equal to 180 degrees, then they must be located between parallels. In the drawing we have line A, this is line B, this is the direct transversal C that cuts those two lines A and B, those 2 points. Those triangles alpha and beta, they are both defined as one-sided triangles. So if the sum of those two one-sided triangles is equal to 180 degrees, that is to say if alpha plus beta equals to 180 degrees, then they must be located between parallels. Then line A is parallel to line B. Likewise, if the sum of those two parallels, if the sum of those two one-sided triangles is equal to 180 degrees, that is to say if gamma plus delta equals to 180 degrees, then it must be located between parallels. That is to say, line A is parallel to line B. We already implemented Rule 20 in our drawing. One put in our drawing, the sum of those two one-sided triangles is equal to 180 degrees, and therefore according to Rule 20, they must be located between parallels. That is to say, AD is parallel to BC. And because of the fact that the big quadrilateral ABCD, side AD is parallel to the opposite side BC, quadrilateral ABCD must be a trapezoid. Because the definition of a trapezoid is a quadrilateral with one pair of parallel sides. Therefore, quadrilateral ABCD is a trapezoid. And again, we should find out that the big quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. What is the of the big trapezoid ABCD? This is trapezoid ABCD. Side AB is parallel to the opposite side CD. Those two opposite sides are defined as the bases of the trapezoid. If the base AB equals to A units and the base CD equals to B units, then the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is actually A plus B times the right edge over 2. Right edge must create 90 degrees with the two bases. It gets 90 degrees here. This is also a right angle. So the height is edge over 2. So in total, the area of trapezoid ABCD equals to the sum of its two parallel bases is actually A plus B times the right edge over 2. Again, right edge must get integers with the two parallel bases. Those two angles are both right angles. Total theory of trapezoid ABCD equals to the sum of its two parallel bases is actually A plus B times the right edge over 2. So it is A plus B times edge over 2. So we can implement the new rule and also find out the area of the big trapezoid ABCD. The area of the big trapezoid ABCD must be equal to the sum of its two parallel bases is actually AD plus BC times the height DC. Why the height is DC? Because of the fact that DC creates those two parallel bases. Those two angles are both right angles. So the height is DC over 2. So in total, we should find out that the area of this big trapezoid ABCD equals to the sum of its two parallel bases is actually AD plus BC times the height DC over 2. And again, the area of the big trapezoid ABCD equals to the sum of its two parallel bases is actually AD plus BC times the height DC over 2. AD is 9, BC is 7, DC is 8. Again, AD is 9, BC is 7, DC is 8. So in total, the area of the big trapezoid ABCD equals to 9 plus 7, that is 16. 8 over 2 is 4. So in total, this question equals to 16 times 4, that is 64. So in total, we found out that the area of the big trapezoid ABCD equals to 64 square centimeters. This is according to the first method of calculation. The area of the big trapezoid ABCD is equal to 64 square units in size. We have another way to find out the area of this big trapezoid ABCD. It is very clear that the area of the big trapezoid ABCD must be equal to the sum of the areas of the four components that it consists of. That is to say, the area of the big trapezoid ABCD must be equal to the area of the first component plus the area of the second component plus the area of the third component plus the area of the fourth component. The first component is the right angle DC, so it is the area of the right angle ADQ, plus the area of the second component, that is the area of this right angle APQ, plus the area of the fourth component, that trapezoid ABCD consists of. The first component is the green triangle PBQ, therefore this plus the area of the green triangle PBQ, plus the area of this fourth component that trapezoid ABCD consists of. The area of the fourth component is actually the area of this green triangle QCB. So in total, we found out that the area of the big trapezoid ABCD according to the second method of calculation equals to the area of the first component, that is the area of the right angle ADQ, plus the area of the second component, that is the area of triangle APQ, plus the area of the third component, that is really the area of the green triangle PBQ, plus the area of the fourth component, that is the area of the green triangle BQC. The next step, we calculated the area of each component separately and then we added all the four areas together. The first component is the area of this right angle ADQ. So the area of the first component is the area of this right angle ADQ. The area of the right angle ADQ equals to the base, that is 2 times the height, that is 9 over 2. 2 times 9 over 2 is 9. So the area of the first component is 9. Likewise, the area of the second component equals to the area of this triangle APQ. The area of this triangle APQ equals to A according to our definition. Likewise, the area of the first component is also A according to our definition. Because the areas of those two areas are equal to each other because of the fact that those two triangles can go into each other. Therefore, they must have also the same areas. Plus the area of the third component, the fourth component that trapezoid ABCD consists of. The first component is the green triangle QBC. So to say, it is the area of the green triangle QBC. The green triangle QBC. The area of this green triangle QBC equals to the base QC, that is 6, times the height CB, that is 7 over 2. 6 times 7 is 42, and 42 over 2 is 21. So in total, we found out that the sum of the areas of those four components that trapezoid ABCD consists of is as follows. Is 9 plus A plus A plus 21. 9 plus 21 is 30, and A plus A is 2A. So in total, according to the second method of calculation, we shall find out that the area of the big trapezoid ABCD equals to 30 plus 2A square units in size. Or according to the first method of calculation, the area of the same trapezoid ABCD is equal to 64 square units in size. So we have two different equations, so they have the same trapezoid, trapezoid ABCD. Therefore, we get the equation 3 that says that the area of the big trapezoid ABCD according to the first method of calculation must be equal to the area of the same trapezoid ABCD according to the second method of calculation. Very simple equation. We only found out that the area of trapezoid ABCD according to the first method of calculation equals to 64 square inches inside, and must be equal to the area of the same trapezoid ABCD according to the second method of calculation. The area of the same triangle, the same trapezoid ABCD according to the second method of calculation equals to 30 plus 2a square inches inside. So in total, according to equation 3, we actually found out that 64 equals to 30 plus 2a. If subtract the 30 from this equation, we found out that here 30 we get cancelled, and we have to leave 2a on this side of the equation, and on the other side of the equation we have 64 plus 30 is 34. In total, we found out that according to equation 3, 34 equals to 2a. If we divide this equation by 2, we found out that a equals to 34 over 2, this is 17. So there are this white triangle APQ is A in A17. Likewise, the area of this green triangle again PBQ is also in A17. And the area of this fourth component is 21. The area of this first component is 9. Our test is to find out the area of this green shape. What is the area of the green shape? The area of the green shape equals to A plus 21. This is 8 is 17 plus 21. This is 38. So in total, we found out the area of the green shape equals to 17 plus 21, that is 38 square inches inside. Okay, thank you very much.